Right, so when you multiply this with an impulse train, you get a signal like this, which has a Fourier transform that is equal to this. Okay. Now, this signal is passed through a filter with impulse response equal to a rectangle. Okay. So a rectangle in the time domain corresponds to what in the frequency domain? Right. A rectangle in the time domain corresponds to a sinc function in the frequency domain. Okay? And since the width of this rectangle is capital T, right, the sinc function in the frequency domain will have 0 points at integer multiples of 2 pi over t, which is omega s. So you will have sinc functions that look like this. Okay? So this signal, when passed through this filter, will be multiplied by a frequency response that looks like this. Okay? So this is let's say this is a x sub p of j omega. Okay? So mathematically, right, this is saying that x0 of t, right, this output here, x0 of t is xp of t convolved with h of t. Xp of t is equal to summation xnt times the delta function at that point. But when convolved with h, right, this is h0, you get h0 moved to that point. Okay? All right, so this is what we mentioned before. Right, when you pass this through this filter, you're moving this to the positions of these impulses, each one scaled by the value of x at that point. Okay, and the frequency domain is just h0j omega times x p j omega. Okay. Now, when you multiply this repeated spectrum by this sinc-like frequency response, this basically distorts the shape of the spectrum, right? Because you're multiplying this spectrum with something with a certain curvature, right? This is not flat. Okay, this is not flat. So you're distorting the shape of this spectrum. So even if you apply an ideal low-pass filter to extract this out, you are extracting out something that is distorted by this curvature, right? So no, it is no longer a perfect triangle, but in fact, the shape changes because you're multiplying by this, non-constant gain. Okay. So what do? One thing you can do is just try to compensate for this loss in your low-pass filter, right? So you can see that this filter gives a larger gain in the middle, a smaller gain in the, on the edge. So if you want to compensate for that, then we can pass it through a low-pass filter that gives a larger gain on the side and a lower gain in the middle to just compensate for this effect. Okay? So this is what you can do. Okay? So you take the output x0 of t, you pass it through this low-pass filter, HR, right? And if you design this HR appropriately, then you should ideally get back a signal that is the same as x of t. Okay? Now, in order to get back a signal that is equal to x of t, then this is saying that the effect of the cascade of these two filters should give you an overall frequency response that is equal to an ideal low-pass filter. Okay? So originally, we know that if we pass it through a filter with an ideal low-pass frequency response, then we can get back our signal perfectly. Okay? So even though this x sub p of t is first passed through something that is not ideal, but if we can multiply it with something that makes the effective response equal to an ideal low-pass filter, then we should be able to get back the same thing. Okay? All right, so the idea is like this, where we want the cascade of these filters, which has a frequency response equal to the response of this one times the response of the second one. And we hope that it is equal to this, which is the ideal low-pass filter. Okay? So we hope that this times this gives you a constant gain between plus and minus omega c and 0 outside of that. Okay. Now, what is the Fourier transform of h sub 0 of t? So it is basically a sinc function, right? But there is a delay. There is a phase shift due to the delay, right? If this was centered at 0, then we just have a pure sinc function. But this is biased, to the side. So we have a phase delay because of this. We have this phase shift because of the time delay. Okay? But anyway, right, with this h0 and knowing what we want to achieve, we can just divide this h0 to the other side to get hr. Okay? So hr is just h of j omega divided by this h sub 0 of j omega. Okay? Right. And this is confined to omega c and minus omega c. Okay? All right. All right, so this is the magnitude and phase of HR. So you can see that HR takes on this bowl shape, right, giving higher gain on the side, lower gain in the middle, to compensate for the lower gain on the side and a higher gain in the middle, right? So if you multiply this with this, then you hope to get back a flat spectrum. Okay? Okay. Now, theoretically, you can do this, but still, it's, again, difficult to realize in practice. Because in practice, it's always difficult to realize perfectly a particular shape of the filter. We can only try to approximate it as much as possible. Okay? So sometimes in practice, right, to avoid having to generate this, this filter for compensating, right, for compensation, what we can do is that we can actually just sample faster, okay? So if we sample faster, then what happens? If we sample faster, then omega s increases. So this is separated further away. And this curve here is stretched out, right? If you sample faster, then this omega s stretches out this main lobe of the sinc function. And therefore, if you stretch it out enough, this curve here will become closer and closer to a flat surface, right? When you just look at this region, it will become closer and closer to a flat region, okay? So sometimes for convenience, you just sample faster and use directly the sample and hold signal as an approximation of the original signal x of t, right? Without having to pass it through another recovery filter, HR, okay? All right, but certainly there's a trade-off here because sampling faster also is more costly, okay? So it really depends on, what cost you are willing to, sacrifice in practice. Okay. Right. So okay, so maybe we can look at an example here. Right. So this is an example of sampling a image. Okay. So this is the outcome of a impulse sampling signal, right? Impulse sampled image. And this is the result of a zero-order hold signal, okay? So basically, for every value here, we're filling it up with a constant block, okay? So we have this mosaic type of, image here. Now, this is with a lower sampling rate, but if you sample faster, right? If you sample faster, as in this case here, then you can see that this actually, approximates the original image pretty well. Okay? So sampling fast enough sometimes, is sufficient. Okay. All right. So other than the zero-order hold, there are also other ways to, to do this with a slightly improved performance in practice. Okay. So for a zero-order hold signal, we're basically approximating this signal with this kind of signal, right? We sample, hold, sample, hold, sample, hold. Okay. But if you were asked to interpolate, if you were asked to recover this signal from the samples, right, without learning anything, the most intuitive way that most people will use is probably just to connect the dots, right? If you are not taught anything, right, and you are given these samples, and you're asked to reconstruct this signal, most people will just connect the dots, okay? So connecting the dots is what we call a first-order interpolation, or so-called linear interpolation. Okay? So this linear interpolation performs the fitting by connecting adjacent samples by a straight line. So suppose you get samples here, then linear interpolation just connects these dots. Okay. Now you can show that this linear interpolation is actually equivalent to the following, right? So suppose that these are the samples, right? These are the samples that you have. Okay. Now, linear interpolation is like moving a rectangle to each one of these samples. So it is like moving a rectangle of width t to each one of these samples and adding them up. Okay? So mathematically, this can be written as a impulse sampled signal convolved with a triangle h of t. Okay? So a triangle h of t can be written like this. Okay? So when t is 0, this is 1. And this decreases to 0 when t is capital T plus or minus capital T. Okay, so it is originally 1, but then goes to 0 after plus or minus t. Okay. Right. So this linearly interpolated signal is this x of r of t, which is the convolution of this impulse sampled signal convolved with a triangle filter h of t, which effectively moves this to integer multiples of capital T, each one scaled by the value of x at that point. Okay. Okay. Now you can try to verify that this is true. Okay, you can verify that this is true. So let's see. Suppose that this is mt and this is m plus 1 t. Okay? All right? And suppose you want to find the value of this point here. Let's say is x of mt plus lambda t, right, where lambda is between 0 and 1. Okay? So suppose I want to find the value of this interpolated signal. I should say xr. Okay, xr. Okay. Suppose this is mt, this is m plus 1t, and I want to see what is the value of xr at time mt plus rt plus lambda t. Okay? All right. So if it is indeed, if it is indeed on the straight line connecting consecutive points, then it should be, lambda times one side of the point plus 1 minus lambda times the other side of the point. Okay? And you can check if this is true. All right, so if you plug this inside, right, if you plug this inside, x sub r of mt plus lambda t. Okay? This will be equal to, x of mt h of lambda t plus x of m plus 1 t h of lambda t minus t. Okay? So when I'm looking at this point, mt plus lambda t, right, I substitute this inside, right? Then every h only extends to capital T on the side. So at the point mt plus lambda t, only two terms will be non-zero, okay? The term where n is equal to m and the term where n is equal to m plus 1, right? So when n is equal to m, you get x of mt times h of this minus mt, so minus mt gives you lambda t, okay, plus x of m plus 1t times h of m of t, mt plus lambda t minus m plus 1t, right? So mt cancels out, so you get lambda t minus t, okay? And then if you substitute this inside here, right? If you substitute lambda t inside here, you get 1 minus lambda, and then lambda t minus t inside here, you get lambda. Okay. So this is x mt 1 minus lambda plus x m plus 1 t lambda. Okay? So indeed, the value of this point is indeed the linear combination of these 2 points, right? The point lying on this line. Okay. So here we have talked about 2 types of practical interpolation schemes. One is by zero order Hode,